Hi everybody. I thought I'd do a video on this problem. I did it during office hours with some people, and this is a really good problem. It's a very challenging problem, but I also think it's a good problem because it really points out the difference between the average quantity and an instantaneous quantity. With multiple variables here, but in particular, it's being very specific about the average power and the instantaneous power. And even people who took physics in the past, if you took physics in the past, we usually just talked about the average power and that was it. But here now we also have instantaneous power, and that's kind of the big new thing here. So this is problem 79 from chapter 7, I hope. Okay, so it says an electron in a television tube is accelerated uniformly. So that's a big thing right there. That means the acceleration is constant, which is nice because that means I can use kinematic equations. Remember, if the acceleration is changing, I got to go back to calculus. I have to use calculus. I got to use integrals or derivatives. But when it's accelerated uniformly, I am allowed to use kinematic equations throughout the problem. Okay, then it says from rest to a speed of, so it starts at rest, right? So that means the initial velocity is 0. That's why I got the initial velocity 0 here on my diagram that I drew. To a speed of something nearing the speed of light, 8.4 times 10 to the 7 meters per second. I wrote that here. I'm calling it V4. I'll tell you why in just a moment. Over a distance of 2.5 centimeters. So I got that distance here. And then it says, what is the power delivered to the electron at the instant that its displacement is 1 centimeter. So it's saying, it's not asking for the average power or the power delivered at the end. It's saying the power at this point right here, which I drew out in my diagram. So here's my origin basically for everything. Here's my 0 mark. And then they're saying 1 centimeter away from where the electron's being ejected from rest. So this is how old television tubes used to be made. You would actually generate an electric field that would shoot the electron off into a screen here, and then you could dictate which way it moves using a magnetic field. You don't need to know any of that, but we'll discover all that come second semester. So I drew my diagram here, and I drew an origin right here, and then here's the screen that the electron is going to hit at the end, and the screen is 2.5 centimeters away. The acceleration is constant, which basically means if the electron starts from rest, it's going to keep going faster and faster and faster and faster. So I'm arbitrarily making these extra velocities, but I want to just point out that the speed is getting greater and greater and greater before it crashes into the screen. So this electron is speeding up, and it's actually gaining energy as it moves, which actually is going to change then the rate of change of power. So in other words, the power, I can't remember if I mentioned it, this is where the 1 centimeter, so this is where we're trying to find out the power right here. But the thing is, because this thing's speed keeps speeding up, so the kinetic energy keeps increasing, the rate of change of power is going to increase as well. Or not the rate of change of energy, which is power, will change as well. So I'm sorry, let me amend that. The rate of change of energy, right? The rate of change of energy, which is power, so I could even say dE dt, is going to change as well. So it means that the power here is going to be smaller than the power here, which is going to be smaller than the power here. So the power is going to keep getting bigger and bigger and bigger and bigger before it hits in runs into the screen there. However, I could just as well take the average power of all of this if I wanted to too. So I guess before I get anywhere, near into this, I want to say, so what essentially is happening here is that, and this isn't, it's the power is not necessarily going to fit a linear line like this, but let's say it does, right? Let's say the power fits a linear relationship. So here's a graph of power versus position right here, and it has this relationship. Not necessarily is this going to be true, but I'm just using this for an example. And basically what I want to try and find out is the power at 1 centimeter here. So if I were to graph that and went, oh, right there, this is what I want, and went over here and said, here's the power, and read it off my graph, that would be my answer. But, you know, unfortunately, I don't have a graph of position versus power versus position, so this is not really going to help me. But let's say then this is the very end, right? This is the very end of where the electron crashes. So this would be the 2.5 centimeter mark, right? And I could get, you know, something here. This isn't going to tell me anything, but it would tell me, you know, the power at 2.5 centimeters when the electron's at the 2.5 centimeter mark. Or if I wanted to, right, and again, I don't need to do this, but I'm just trying to show the difference. I could, you know, look at kind of, you know, here's the initial power, here would be the final power, right? And I could then look in between, and this would be the average power. So if I read off this would be the average power. But again, that's not what I'm looking for either. But I want to use this graph to hopefully be a nice visual that's going to help us look at kind of the equations that I'm going to show later on. Okay, before I go any further as well, I want to say, do I want to start there? No. Yeah, what the heck, let's do it. Okay, so the acceleration is constant, right? And that's due to a constant force then, because the acceleration is constant. That's why it's constantly speeding up. And that would be due to a constant net force. So I'm going to say, here is my, you know, here's my electron at any moment. There would be a net force accelerating the electron this way, and I know that because the acceleration's constant. So it's essentially using Newton's second law, F net equals ma. So if the mass of the electron is not going to change, and in fact the mass of an electron I can look up, the mass of an electron is 9.11 times 10 to the negative 31 kilograms. This is constant. They've told me that in the problem. Therefore, if the mass is constant and the acceleration is constant, the net force is also constant. So I just want to establish that as we keep going here. Okay, so next up, I'm going to now use this. Let's talk really briefly about average velocity and instantaneous velocity as well before I go any further. So again, the average velocity is pick any 2 points, any 2 positions, and divide it by the time it takes that object to travel to those 2 positions, and you'll have yourself an average velocity. Now, if you wanted to find out what an object's velocity at any instantaneous moment is, that's what we call the instantaneous velocity. And the instantaneous velocity is the notation we use is dx dt. And this dx is saying a very small change in position, like super duper duper small. And then dt is a super duper duper small change in time. So, and if I took those 2 ratios, that would be the instantaneous change in position over the instantaneous change in time. Okay, so in the video I showed you guys, I talked about power being the average, the change in energy over and this would be the average power is the change in energy over the change in time. And so I also then said, okay, well, let's just kind of, so also I said change in energy is equal to the work done, right? Any work done will change the energy. Any work done on a system will change the energy of that system. So you could also write power as being power equals the work done over the change in time. Well, again, average work is force times distance. Let's use displacement. And so I could replace that with the work, and then I get power equals force times displacement over delta t. And then in the video I said, hey, wait a minute, delta x over delta t, that's the average velocity, yo. So basically this is a way that you can get average power. So, and I'm going to kind of simplify some of this, is that I'm going to say average power, well, that's going to be the average force then multiplied by the average speed. So the thing is that I could do this same thing. So again, here's the force, is that I could do this with the instantaneous power as well. So I could say the instantaneous power then would be the instantaneous force, the force at any particular moment, right? The instantaneous force. And instead of saying delta x over delta t, I could say, get really specific and say dx dt. So this would be dx over dt, and do this same thing. And this basically becomes the instantaneous power would be equal to the instantaneous force multiplied by dx dt, which is the instantaneous velocity. And so you got these two different ways of looking at it. So if I'm looking for the average power, well, I could take the average force multiplied by the average velocity, and that would give me the average power. That's the, and then, or if I want the instantaneous power at any moment, well, I would need to find the instantaneous force and multiply it by the instantaneous velocity. Yeah. So, and the reason I have this is so if I said, hey, I want to find out what the average power is from 0 to 2.5 centimeters, I would use this equation. But what this would calculate for me then is I would try and find out, or you know what, let's start instead with here. Let's say I absentmindedly went, oh, okay, velocity, well, here's a velocity. I'm just going to plug this velocity into here and then multiply it by a force and get my power. Well, the thing is, if I did that, if I found that velocity and say multiplied it by a force, ma, or something. Let's say I got the force. I'll talk about getting the force later. Let's say I got the force and I multiplied it by that velocity. I would be wrong, because if I multiply it by this velocity, I will get the power at this particular moment when at v4 when the electron is about to crash into the screen. I'm basically kind of confusing both average and instantaneous because, well, yeah. So that's not going to work. Or let's say so that would be the power at, so if I plugged in, that speed, that would be the power. So if I plugged in this speed like this, that would be the power at the position 2.5 centimeters. So which is not correct. That's not what I want. Well, let's say I got a little clever and I said, well, wait a minute. Average power then from, this is an average power equation. So if I want to find out the average power from 0 to 2.5, well, then I need to find the average velocity, right? Here's 1 velocity, 2 velocity, 3 velocity, 4. I need to find out the velocity in between here. And they told me the acceleration is constant. So if that's the case, I could use that average velocity definition, just the flat out definition of average velocity. What do I want to use this in? Let's do this. So that would be the initial velocity plus the final velocity, so it'd be the velocity of 4 divided by 2. So if I found that velocity and then plug that in there and then multiplied that by my average force, I would get the average power. That would be correct then. I would get the average power, but that would be then the power, that would be the power throughout this whole thing. Again, that would be the power in between here, right? So if I were to, again, going back to the other way, if I were to plug this velocity into that equation, if I were to plug this velocity into this equation, I would be getting the power here. But if I were to plug in this average velocity into this equation, I would be getting the power here. I don't want either of those. I want the power at 1 centimeter. This is what makes this problem challenging. Okay, so let's then instead go here with this instantaneous thing here. And already I can use, so it's the instantaneous power. Already I can use the fact that what's nice is the force is constant throughout this whole problem. Why? Because the acceleration is constant throughout the whole problem. We've established this already. So the instantaneous force at 1, the instantaneous force is the force throughout the whole problem, because the force is constant because the acceleration is constant and the mass is constant, right? So I can just basically plug in mass times acceleration. I can replace this with mass times acceleration. So it'd be the mass of the electron times the acceleration of the electron. But now I need to find out the instantaneous velocity. And what is that velocity based off my diagram? I called it V2 here. So I'm saying these are lined up like this. So the velocity V2, so that's the instantaneous velocity I'm trying to find, right? Which would be different than plugging in what I did before of plugging in V4. That's not correct. So I want it at V2. So in order to get V2 though, again, the acceleration is constant throughout on this problem. So I can use kinematic data. So that's where I'm going to go to next, which is down here. So I'm going to act like, hey, I'm going to start here. And I'm going to say my initial moment, you always want to establish my initial moment is when the electron's at rest. My final moment is here when the electron is at 1 centimeter mark. So, okay, let's plug in what I can. So if the initial, these are instantaneous velocities, by the way, right? These are velocities at certain moments. And these are instantaneous positions here. So my initial velocity then, when the particles at when the electron's at rest is 0. V2, I don't know that. This is essentially what I'm looking for. This is the big thing that I'm looking for. So if I can find this, I got this. Acceleration, I don't know, but hey, I actually kind of need this, so that'll be something nice to do. The initial position I'm saying is 0. The final position is 1 centimeter, so it's 0.01 meters. And then time I don't know either. So I really only know a few bits of information, and actually I'm not going to have enough information to solve yet. So what I'm going to do is I'm going to change my position, my final moment, from being here to actually being over here, with the idea that I'm going to use this. So my final moment is now going to be at V4. So my reasoning for this is I'm going to use this to find the average velocity. And once I find the average velocity, I can then, so once I find the average velocity here, that's the same average velocity here. Because again, the velocity is constant throughout the whole problem. So that's what I'm going to do. Let's see if this works. And then it's going to be all downhill from there. So, okay, here's my final velocity now at this moment. So again, my initial velocity is 0. My initial position is 0. But now I know my final position is 2.5 centimeters. That's 0.25 meters. And I know my final velocity, they told me at this point, is 8.4 times 10 to the 7 meters per second. And now I'll be able to calculate the acceleration. So I'm going to use v4 squared equals v naught squared plus 2a, and then I got my final position minus my initial position. So my initial velocity is 0, my initial position is 0. And so I'm going to isolate for acceleration. Isolating for acceleration leaves me with v4 squared over 2 times x4. That's going to be my acceleration. So v4 is 8.4 times 10 to the 7 squared. Divided by 2 times 10 to the 4, which is 0.025. And this gives me an acceleration of 8.4 times 10 to the 7 squared divided by 2 times 0.025, 1.41 times 10 to the 17. Now, this is a huge acceleration, but hopefully that makes sense. We're accelerating an electron in 2.5 centimeters to almost the speed of light. So that takes a lot of acceleration. So, and there's no limit to acceleration. There's a limit to the speed of light. We'll talk about that in a moment. I think that's 17. I think that was right. Yep, 17. Okay, and so now that acceleration is going to be my acceleration over here, right? Because again, the acceleration is constant. So the acceleration is constant. So there we go. Now I got the acceleration. Now I can solve for what I was looking for here. So let's do that now. So now I'm going to do v2 squared equals v naught squared plus 2a x2 minus x naught. So again, initial velocity is 0. Initial position is 0. This is going to be v2 squared equals let's take the square root. So take the square root. We can plug in 2. The acceleration is 1.4 times 10 to the 17 meters per second squared, and then multiplied by my position, which is 0.01. I would parenthesize everything like crazy. Do the square root and then open parentheses. Put this in parentheses, put that in parentheses when plugging into your calculator, because your calculator is an idiot, and it can do some fancy things, but you need to tell it how to do order of operations and things like that. So 1.41 times 10 to the 17 times 2 times 0.01, and then square root. And that gives me, I'm getting 5.3 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7 meters per second. Always a good idea to check, is the speed under the speed of light? So the speed of light is 3 times 10 to the 8. If it's less than that, that's good. So that's good. It is less than that, because if not, we would be making a mistake. So that is V2. So now I got V2, and I even got my acceleration as well, all in the same effort right there. So basically now I can take those and plug those in for my instantaneous velocity and my acceleration. So in fact, I'll stop calling this P instantaneous. I'll call it P2 because it's the power at position 2. That's going to be the mass of an electron. The mass of an electron, like I said before, and you can look that up, is 9.11 times 10 to the negative 31 kilograms. The acceleration I got was 1.41 times 10 to the 17 meters per second squared. And then the instantaneous velocity was 5.3 times 10 to the 7 meters per second. And so lastly, plugging all this in. So I got 9.11 times 10 to the negative 31 times 1.41 times 10 to the negative, or positive 17, sorry, that's a big number, times 5.3 times 10 to the 7, and I get, I'm getting 5.5 times 10 to the negative 6. And that's watts right there. And then I think in the back of the book, they use, because times 10 to the negative 6, if you wanted to put that in a little more concise terms, that's a microwatt. So this is also the same thing as 5.5 microwatts. So that's the same thing though. So yeah, again, challenging problem, I agree, but also does a great job at kind of pointing out the difference between instantaneous things and average things. So hopefully that helped. All right, take care. See you guys. Bye.